Since it's 2 o'clock now, I guess it's time to start this afternoon session. So the first talk will be given by Professor Patrick Cheridito, and he will talk about deep splitting method for SPDs. The stage is yours.
Okay, thanks so much. I also want to thank the organizers for putting together this interesting workshop and letting me participate. So this is based on work with Christian Beck, Sebastian Beck, Balint Gersay, Arnulf Jensen, and Ariel Neufeld, who at some point in time all were at ETH Zürich. So deep splitting combines operator splitting and deep learning. And so here we apply it to solve parabolic PDEs. For example, linear PDEs such as heat equations, Black-Scholes equation, or also nonlinear PDEs like nonlinear heat equations or also nonlinear Black-Scholes equations, which have become more widespread since the financial crisis because people usually now also incorporate transaction costs, constraints, credit risk, model risk, and other frictions. Can also be used to solve Hamilton-Jacobi Bellman equations, Allen-Kahn type equations, Sine-Gordon type equations, and it can also be used to solve stochastic PDEs, for example, heat equations with noise, or also nonlinear heat equations with noise, or stochastic PDEs that appear in the theory of stochastic filtering, such as Sakai equations and Kushner equations. So then there are other examples, but the examples that are listed here are examples that we actually implemented. So the parabolic PDEs that we're looking at are of this form. So there is a partial derivative with respect to time. Then there is an f function applied to x, u, and the gradient of u. And then there is a linear second order term. Time ranges in some interval from 0 to capital T. X is in RD, and D here possibly is high dimensional. Okay, so we do up to 10,000 dimensions actually. Phi is the initial condition. Sigma is a mapping that maps RD into the matrices, the D by D matrices. And this function capital F so far is a general nonlinear function, which we decompose into a linear part and then another linear function, little f. Okay, and this decomposition, of course, is not unique, but the idea is that you're given capital F, and then you try to separate the linearity as large as you can, so as to make the remaining nonlinearity, little f here, as small as possible. Okay, so the idea is to decompose this nonlinearity, capital F, into another linear term and the remaining nonlinear term, little f. Okay, and then to shortly explain what the numerical method does, I'm writing the PDE first in integral form. So I'm writing u as the initial condition plus these two integrals. And then I'm decomposing capital F into little f. So that's my nonlinearity. And into this linear term involving the mu coefficient here. Okay, then I'm discretizing time. And then I'm freezing the nonlinearity, little f, over every little time interval. Okay, so locally, this is now a linear PDE that I'm trying to solve. And so this is called splitting, and it has been studied before. And under suitable assumptions, it can actually be shown that the error here that you make by locally linearizing this equation like this is 1 over n, if n is the number of time steps. Okay, but this assumes that you can actually solve this locally linear equation that I wrote for V here, which is not obvious how well you can do it if the dimension D is high. Okay. So then once we locally linearize the equation, we use Feynman-Katz representation locally. So we introduce a diffusion process Y defined by the coefficients mu and sigma. And then this diffusion process y is running in the opposite direction, okay? And then we're calculating v at the first time increment t1, and the value the process takes at time capital T minus t1 as a conditional expectation given the state of the process y at this time. Okay, so this is the first little time increment, and then we do iteratively the same for the other time increments. Okay, so this theoretically solves the locally linearized equation. But of course, numerically, we now are left with approximating these conditional expectations, which is non-trivial in high dimensions. Okay, and the idea here is to approximate these conditional expectations with the parametrized family of functions v that are parameterized with the parameter theta here. So then I'm going to approximate the first conditional expectation by v parameterized by the first parameter theta1, and so on over the other time steps. Okay, so numerically, how am I going to do this? Well, the conditional expectation is an projection in the space of square integrable random variables. So if I have a random variable, a y over here, and this blue set here is the square integrable random variables that are measurable with respect to x, or the sigma algebra generated by x, where x can be a high dimensional random vector here, then the conditional expectation is the best L2 projection. Okay, and so it can be formulated as a square minimization problem. Okay, so the conditional expectation minimizes this expected square distance here, where in theory, the function psi here is going over all Borel measurable functions psi from Rd to R. Okay, so since in practical applications, you will not be able to evaluate this expectation explicitly here, you're going to generate Monte Carlo samples of the pair xy, and you're going to minimize this empirical mean square distance, okay? And you're also not going to be able to minimize this over all possible Borel functions, so you're going to restrict on a subfamily S here of all possible Borel functions, okay? And so typical choices are all functions that are linear or affine in the underlying x components, or are polynomials, or splines, for example, okay? Whatever you're going to do is you're not going to compute exactly the conditional expectation, but you're going to land somewhere in this blue set here, okay? So I denoted this by this psi hat, the estimation of psi, which is not the correct conditional expectation, but is being somewhere in this blue set here. And the distance to y is larger than it theoretically is. Okay, and so what we're going to do here, instead of using linear polynomial or spline regression, we use neural networks to do this least square Monte Carlo here. Okay, and so we use straightforward feed-forward neural networks of this form. So most of the time we use 2 hidden layers, but you could also use more or less. So then it's just, this neural network is just a composition of affine and nonlinear transformations. Capital D is the depth of the neural network. So here it would be 3, so it has 2 hidden layers. Then the Q's denote the numbers of hidden neurons. The A's are the affine transformations. And the parameter consists of all the components of the matrices and vectors that you're using to represent your affine transformations here. And phi is a nonlinear activation function. So typically it's the hyperbolic tangent, or the so-called ReLU activation function, but it can also be something else. And so then you will have this many network parameters in your network over which you have to solve your minimization problem. And you're typically going to use a stochastic gradient descent method to train the network. Okay, and so to show you how this works in an example. So first we solve this stylized Hamilton-Jacobi Bellman equation, which is just the Laplace minus the square of the 2 norm of the gradient. So this has the form of a Hamilton-Jacobi Bellman equation. So you can also solve more complicated Hamilton-Jacobi Bellman equations. So typically here you have a concave function in the gradient. So we chose this particular form here, as other authors did before us, because this equation can be transformed into a linear equation that you then can solve with standard Monte Carlo to obtain a reference solution. Okay, so the initial condition we chose here was just the square root of the 2 norm here. And what I'm showing you here is numerical approximations of the value of the solution u at capital T for t equal to 1 and 24 time steps. Okay, and so these are the results. And as you can see, we do this for very high dimensions from 10, 50, 100 up to 10,000 dimensions. The runtime in seconds remains manageable. So even though we use GPUs here to run, to do the training here. And as I already mentioned, so we transform this equation to obtain a linear equation to be able to compute reference solutions to which we can compare. And in this column here, you see relative L1 errors of the solutions, which are very small. Okay, then as a second example, I'm showing you a semilinear heat equation. So it's the heat equation with a nonlinear term here. Okay, the initial condition is this one. And I'm showing you approximations of the function value again at time capital T for t.3 here. And space 0.0 for 20 time steps now. Okay, and then again, we solve this in very high dimensions, up to 10,000. The average runtime in seconds remains manageable. We also solve this same example with an alternative method, which is multi-level Picard method here from this paper of Hutzenthaler and co-authors. And the relative error again is small. Okay. Then I'm also empirically want to check how this behaves when I increase the number of time steps that I'm taking here. And so here in the first, so this is all in 100 dimensions now. So, but in the first columns, you see 1, 2, 4, 8 up to 32 time steps, okay? And you see the relative error empirically more or less decreases like 1 over n. Okay, so this is not a theoretical result. This is just empirically what we observe. Some of the advantages of deep splitting compared to other methods that also work well, and some of which also have been presented in this workshop here. So the deep splitting method divides the PDE approximation problem into a sequence of separate learning problems, because in every time step, I only need to calculate one conditional expectation. So I only need to store the function value at this time and then compute it one time step after that. So therefore, it can handle very high dimensional PDEs, and it also doesn't really have a constraint on over how long a time interval you can use it. Secondly, it also can be extended to stochastic PDEs. Okay, and just to give you, rather than give you an abstract form here, let me give you a concrete example here, which is a Sakai equation, which comes from having a d-dimensional signal process y and a d-dimensional observation process, which is a possibly nonlinear function of the y process perturbed by some noise v. And then in stochastic filtering, the goal is to recover the unconditional or the conditional distribution of y given the observation c. And it's given, the unnormalized density is given by the Sakai equation, which in this example is given here, x. And so this is a stochastic PDE now. So the first term is a partial derivatives. And here you have a noise term, which is the observation process. Okay, and so you can use exactly the same method, pathwise conditioned on the observation process C. And so again, I'm giving you numerical results here for the approximation of X capital T at 0 for T.5, 25 time steps, and 5 different realizations of the observation process C. Okay, so this is a bit harder now to compute, but we can still do this up to 50 dimensions quite easily. And so here we specified the Sakai equation so that we could transform it into a PDE with stochastic coefficients, which again gave us a reference method, an alternative method to compute reference solutions. Okay, and so what you see here is in each dimensions, 5 realizations of the observation process C and the corresponding results, and also the relative errors compared to the reference method is relatively small. Okay, so this was the method, and also some indications that it works well in very high dimensions. So as I already mentioned, so there are classical results that give error estimates on the splitting method, but the Achilles heel somehow here in what we're doing is computing the conditional expectation in high dimensions. So in the last part of this presentation, I want to talk about conditional expectations. So as we saw, they are L2 projections. So theoretically, I would like to minimize this expected square distance over all Borel measurable functions psi here. But typically, I'm not going to be able to calculate this expectation. So I'm going to approximate the true regression function psi bar by psi hat, which is a minimizer of the empirical square distance problem here. Okay, and again, I'm not going to be able to do this over all Borel measurable functions, so I'm going to do this over a subfamily S. Okay, and so if you do this, you at least make 3 mistakes. So one mistake is a statistical error, which comes from approximating the true expectation with this empirical mean here. But in the setup we are here, simulation is quite cheap. So this first error is not a major concern to us because we can choose the M in the empirical average here very large. Okay, so the second error is going to be a function approximation error, okay, because the true regression function might not be in the subfamily S that you're minimizing. So it might not be a linear function, might not be a polynomial function, and it might not even be in this class of neural networks that you're parameterizing over. Okay, and lastly, you're also going to make a numerical error, especially if you're training a neural network, because typically you're going to use a stochastic gradient descent, and it's not always clear what the stochastic gradient descent is converging to, if it's converging at all. Okay, so what I want to do here, instead of analyzing these 3 errors here, I want to derive a posteriori guarantees. Okay, and so the idea is the following. So let me assume I have trained my neural network and I have a candidate regression function psi hat that I'm fixing now. Okay, then this u is the theoretical square distance from y using this psi hat, which is above the minimum, which I'm going to denote by d here. Okay, so since, like in contrast to supervised learning, I'm not going to be able, no matter how much I train, to reduce this error to 0, right? Because the minimal error that you can approximate this to is the error from y to the conditional expectation of y. Okay, and so what you have is this upper bound u. How tight is this upper bound? And so my idea now is to get an estimate on how tight this upper bound is, okay? And so what I'm going to do is I'm going to use this assumption that y is of the form, y is the function h of x plus some additional noise v, which is independent of x. Okay, so this is not really an assumption in the sense that this is always satisfied. For any y and x, you can like write y theoretically in this form. The point, I mean, for my method to work is that I need to know h explicitly. Okay, but in these PDE approximation problems that I solved you, I know the function h. Okay, and then I'm going to define C. And I'm going to introduce additional randomness V. So I'm going to introduce an independent copy V tilde of this V, random variable or random vector. Okay, and then it's not very hard to show that even if you don't know the theoretical regression function or the theoretical form of the conditional expectation, you can write the 2 norm of the conditional expectation as this expectation. And you can write the distance of the conditional expectation from y as this expectation. Okay, why is that good? Because these latter 2 expectations can easily be approximated with standard Monte Carlo averages. Okay, and then by Pythagoras, you get that this distance squared plus this distance squared is the distance y minus your candidate regression function. Okay, and this gives you an estimate on the error you're committing when you're approximating the conditional expectation with your candidate regression function psi hat. Okay, and what I have here on the right-hand side, so the left-hand side is my L2 approximation error squared. And on the right-hand side, I have basically 2 expectations which I can easily estimate with standard Monte Carlo. Okay, and so let me shortly in the remaining time give you 3 easy examples. So my first example is, and so now this is a bit decoupled from the PDE example, but you can do exactly the same thing for the PDE example. So here I'm doing first a baby example. So I want to compute the conditional expectation of y given x. And I'm going to assume x has 4 components, x1 to x4. And they're all independent standard normal. And I'm writing y as this polynomial of the x components, and I'm adding a noise term v, which is again the independent standard normal. Okay, so obviously the conditional expectation here is just this polynomial in the x component. So I chose this example explicitly so that I could compute the conditional expectation. And the distance of y, of the conditional expectation from y, is exactly 1. Okay, and so let me see now how that works when I am applying my computational method now. So first I'm going to try to find my regression function with a linear regression. Okay, and u is the upper bound and d is the estimate of the true L2 distance of y from the conditional expectation. Okay, so in all the examples, d is the same, is around 1 as it should be. Okay, u is not tight at all, okay, because with a linear regression, meaning just with linear functions in x1 to x4, you're not going to be able to approximate this polynomial expression very well. The relative error of the L2 approximation error of the conditional expectation with your candidate regression function with respect to the 2 norm of the true conditional expectation is 77%, okay. Then let's try a second order polynomial regression, which is a bit pointless because we know it's going to solve the problem correctly because the problem is polynomial. Okay, so but you see from the numerical results, the upper bound is very tight and the relative error is 0.6. Okay, and then I'm doing the same exercise with a ReLU neural network and a hyperbolic tangent neural network, and the results are comparable to the second order polynomial regression, which is kind of the best method here to use. Okay, then my second example is more complicated. So now I try to compute y given x, where y is this complicated function involving lower hyperbolic tangent of 5 x components and 5 independent v components. Okay, so now you're not able to calculate the conditional expectation explicitly. So let's see what the numerical results give. So again, the linear regression is not doing well here. So the relative error is 100%. The second order polynomial regression is better, but it's still giving you a relative error of 30%. And the two neural networks, if you choose them large enough, and if you train them well, give you good results. Okay, so with both, we achieve a relative error on the 1% here. Okay, and then as a last example, I'm looking at the financial example. So I'm looking at the payoff of a 100-dimensional knockout option. Okay, so I'm assuming I have 100 stock prices which follow these geometric Brownian motions with possibly correlated Brownian motions. And I want to compute the conditional price of a knockout option, which is a discount times some fixed value C, for example, 100 or 1,000 British pounds, given that none of the stock prices goes below some barrier. Otherwise, the option so-called knocks out. Okay, and so this is a complicated expression that might appear in a computational finance problem. And so let's see how that works here. So the linear regression is not doing so badly. So it is able to approximate this with a relative error of 2.8%. The second order polynomial regression is a bit better, no, but not much better. And again, the two neural networks, if they're chosen correctly and if they're trained appropriately, also give good results here in 100 dimensions. Okay, and so these are the references. So the first is a paper where we implement the deep splitting method for parabolic PDEs. The second one is a paper where we implemented the same method for stochastic PDEs. And the last paper derives these L2 a posteriori guarantees for conditional expectations.
Thank you very much for this very interesting talk. Are there any questions? So maybe I might start with a question. So if I understand correctly, the idea of the method was to have an evaluation of the solution at just one specific time and, for instance, the origin. But what would actually happen if we're interested in a very large number of spatial points where we want to evaluate the solution? Does this mean we have to repeat the same procedure over and over again, or can we somehow simplify the procedure for evaluating solutions?
Okay, yeah, thanks very much. So yeah, you can just train one neural networks that gives you the function, the solution of the PDE as a function of time and x if you want, though it's restricted on a time grid. So here I just showed you numerical values for one particular t and x value, but you can train a neural network for all possible t and x values.
Okay, thank you. Are there any other questions?
Can I ask a question?
Yes, sure.
You had a very nice talk. So I'm wondering, like, so when you apply the deep splitting method for in the intermediate time step to compute the conditional expectation, you need to know the sample distribution of your x, right? And I think that's defined by the forward SD.
Yes.
So in that case, if the parabolic PD becomes quasi-linear, then that expectation, that means the distribution is also unknown. Like, have you tried the deep splitting method for the quasi-linear case, and how do you deal with the unknown distribution of forward x? Because in the quasi-linear case, that might also involve unknown terms.
Okay, thanks for the question. So first I have to say, no, we didn't try for quasi-linear. So the examples that we implemented, I showed you. Then just for everybody to see, yes, you're simulating this Y process here, right? So you simulate it, for example, by time discretization and by some Euler-Maruyama scheme, or, I mean, in many cases, this is just a linear Brownian motion or an exponential, so you don't even have to approximate it. And so once you have this, you're going to calculate conditional expectations step by step by this squared expectation minimization problem. So now I didn't fully understand what the problem was with the quasi-linear case.
Yeah, I mean, I guess the question is that in this Feynman-Katz orientation, in order to compute the conditional expectation, you need to sample Y, right? You know,
Yes.
You need to know where you want to compute Y.
Yes, you just compute samples of Y.
Yeah, so how do you get the samples of Y? That's my question.
Okay, you simulate W and then you discretize. So in the general case, you simulate W and you discretize this equation for Y, and then you use
I mean, how do you know that? I guess my question is, how do you know the distribution of Xi?
Xi, okay, good question. And it actually relates to the first question. So if I want to calculate my solution U just at one single point at the fixed time, capital T, I'm choosing this Xi here equal to this one fixed point, and I'm simulating this up to capital T. So, but alternatively, you can choose Xi as a distribution, a normal distribution, for example, and then you sample from this normal distribution, and then you train a full neural network at that time, so which gives you then values for all different Xis.
Okay, I see your point. Thanks.
So maybe I can explain it here. So in this last equation, so in this equation here, so if you're calculating V at time capital T, you will have YT capital T minus capital T, okay? So you're conditioning on the first, on Y0 here, okay? And so if you want to calculate your solution at one specific point, you're going to start your diffusion from this specific fixed point. But alternatively, you can calculate your solution for all possible space variables. So you're just going to start your diffusion at some initial distribution and you sample over it, and then you're going to learn the whole neural network.
Thank you very much for those additional explanations. I think in the interest of time, we have to move on to the next speaker now. But let's thank Patrick Cheridito again for his very interesting talk.